Section 8.1 Part 3 Distribution of Sample Mean. Lesson Objective: Compute problems involving the central limit theorem. If you recall, the central limit theorem states sample size of n greater than or equal to 30 are drawn from any population with mean mu and standard deviation sigma. Then the distribution of the sample means, x bar, approximates a normal distribution. The greater the sample size, the better the approximation. If the population itself is normally distributed, then the sampling distribution of the sample means is normally distributed for any sample size n. In either case, the sampling distribution of the sample means has a mean equal to the population mean. The sampling distribution of the sample means has a standard deviation equal to the population standard deviation divided by the square root of n. This is called the standard error. Here's a visual. So for any population distribution, the distribution of the sample means for size n greater than or equal to 30 will become normal. Its mean will have the same mean as the population, and the standard deviation will be smaller. If the original population is normal, the sampling distribution of the means for any sample size will become normal, will have the same mean as the population mean, and the standard deviation will be smaller. To transform x bar to a z-score, we use this formula. So we take our x bar, we subtract our mean, and then we divide it by our standard deviation. Let's do an example. Based on tests of the Chevrolet Cobalt, engineers have found that the miles per gallon in highway driving are normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. A. What is the probability that a randomly selected Cobalt gets more than 34 miles per gallon? Okay, this is a Chapter 7 problem. First thing we want to do is draw our picture. Our mean is 32. We're interested in the probability of getting more than 34, so this is area to the right. We need to change 34 to a z-score. So we take our value minus the mean and divide it by the standard deviation, and we end up with 0.57. Using table 5, we look up 0.57, and it's 0.7157. We have to do 1 minus this number because we want area to the right. So 1 minus 0.7157 is 0.2843. Part B. 10 cobalts are randomly selected and the miles per gallon for each car is recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? And now we're talking about a sample of 10. So now we're going to look at the distribution of the sample means. So we know that the mean of the sample means is equal to the population mean, 32. And we know that the standard deviation, called the standard error, actually gets smaller, and it's 3.5 divided by the square root of the sample size, 10. So we draw a picture. Again, we are interested in exceeding 34 miles per gallon. We need to change that to a z-score. So we take our x bar, we subtract the mean, and then we divide it by the standard error, and we get 1.81. Using table 5, we have to do 1 minus 0.9649, and we end up with 0.0351. Part C. 20 cobalts are randomly selected and the miles per gallon for each car is recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? Would this be unusual? Why? Just as before, now we are talking about a sample size of 20, so we have to look at the distribution of the x bars. So again, the mean of this distribution will be equal to the population mean. The standard deviation is actually going to get smaller. It's 3.5 divided by the square root of 20. We draw our picture. We change this 34 to a z-score. It's 34 minus mean divided by the standard error. We get 2.56. Using table 5, we look up 2.56. We see it's 0.9948. We have to do 1 minus that probability because we want area to the right, which is 0.0052. Now, is this result unusual? Yes, this is less than 5%. This is a very small number. So as the sample size increases, getting values that are away from the mean, the probability of that happening becomes smaller and smaller. Let's look at another example. According to this website, the mean ATM withdrawal is $60. Assume that the standard deviation for withdrawals is $35. If a random sample of 50 ATM withdrawals is obtained, describe the sampling distribution of X bar, the mean withdrawal amount. Since our sample size is 30 or more, it's 50. We know that from the central limit theorem, the distribution of X bar is normally distributed. That's its shape. Its mean will be equal to the population mean 60, and the spread, the standard deviation, is actually going to get smaller. It's 35 divided by the square root of 50. Part B, determine the probability of obtaining a sample mean from the 50 randomly selected withdrawals of a withdrawal amount between $50 and $60. We draw our picture. We want the area in between 50 and 60. We have to convert the 50 and the 60 to a z-score. This one turns out to be a negative 2.02. The second z-score turns out to be a z-score of 0. It's actually the mean. And if you remember to find the area in between two z-scores, we look up the largest z-score and the smallest z-score, write those probabilities down and subtract them. So if we look up the probability of being less than 0, that's 0.5. Probability of being less than negative 2.02, according to table 5, is 0.0217. To find the area in between, we subtract these two probabilities, and we end up with 0.4783. Part C, determine the probability of obtaining a sample mean from the 50 selected withdrawals of an amount of at least $100. At least means greater than. So we draw our picture. Here's 100. We want area to the right. We change 100 to a z-score. We end up with 8.08 for a z-score. Using table 5, we see that 8.08 is not on the table. We have to use the default of 0.9999. And since we want area to the right, we do 1 minus 0.9999, which is 0.0001. Let's look at our last example. The new Lucky Lady Casino wants to increase revenue by providing buses that can transport gamblers from other cities. Research shows that these gamblers tend to be older, they tend to play slot machines only, and they have losses with a mean of $182 and a standard deviation of 105. The buses carry 35 gamblers per trip. The casino gives each bus passenger $50 worth of vouchers that can be converted into cash. So the casino needs to recover that cost in order to make a profit. A, find the probability that if the bus is filled with 35 passengers, the mean amount lost by a passenger will exceed $50. We're dealing with a sampling distribution of size 35, so we know the mean is equal to the population mean, $182, and the standard deviation is 105 divided by the square root of 35. If we draw our picture, here's our mean, 182. We're interested in exceeding $50, so that's area to the right. We change 50 to a z-score. 50 minus the mean divided by the standard error, and we end up with a negative 7.44. Using table 5, this value is not in the table. We have to use the default 0.0001, and we want the area to the right, so we have to do 1 minus, which is 0.9999. So the probability that if the bus has 35 passengers, the mean amount lost by a passenger will exceed $50 is 99.99%. Based on this result, does the casino gamble when it provides such buses? Clearly no. There's a 99.99% chance that they will make a profit. So it's not a gamble for the casino. Thanks for watching.